Okay, so in this video, we're going to talk about something called the intermediate value theorem. This is one of the big theorems that we do need to be comfortable with working with for the AP test. It's one of the three major theorems that we'll see this year. So let's first of all define this, and then we'll see if we can visualize it. As I've said we talked about the squeeze theorem, although it's not one of our major theorems. If you can visualize what's going on with the theorem, a lot of the work for it comes together. So here's what the intermediate value theorem says, and you can always abbreviate it IVT. It says, first of all, you must know that the function that we're looking at is continuous along the closed interval from A to B. If this condition is met, then what we can say is f of x will take on every value between f of a and f of b at least once along the interval. Okay? So if we are continuous from a to b, then our function will touch every single value between f of a and f of b at least once along the interval. If you draw a picture with this makes sense. Okay, so let's draw ourselves a little picture. Let's say that this point was sitting at a comma f of a, and then let's say we had another point over here that was at b comma f of b, and we knew that we were continuous between these 2 points. What this theorem says is all these y values that are in between f of a and f of b, if this is f of a right here, and this is f of b, we have to touch every y value at least once between these 2 points. And this makes sense because if you connect these 2 points, no matter how I connect them, doesn't matter if I have this going on or if I just have something almost linear, I have to touch all of these y values at least once between these 2 points. Now we could touch them more than one time, but there's no way that we can get from the first point to the second point if it's continuous without touching every single y value in between where we start and where we end. So that's the intermediate value theorem, and you can use it for a few different things when it comes to solving equations. Basically, you can use this as a guaranteed existence theorem for a solution to some sort of equation. So let's go ahead and let's look at some different problems here. First of all, one question that I'd like to ask is why does the continuous part matter? Okay, because you should always think for a theorem, for most theorems, some initial condition must be met to even start thinking about the theorem, and we should wonder why does that initial condition need to be met. So let's say that I pose this question. Let's say I said, does the intermediate value theorem guarantee that f of x equals 0 for some value for f of x equals 1 over x between -1 and +1. Okay, so basically we're wondering, does the intermediate value theorem guarantee that we're going to touch y equals 0 for some point for the function 1 over x between -1 and 1? And if a lot of students ignore the continuous part of the beginning, here's what they'll do. They'll say, well, f of -1 is -1, and f of +1 is +1. So they'll say, well, f of x equals 0 is somewhere in between -1 and +1. All right, so they'll say, yes, the IVT guarantees this. Okay, however, this is wrong, because just think about this graph for just a moment. If I drew this graph, maybe you don't remember this off the top of your head, but maybe you could plug this into a calculator and you can see what this looks like. This is what we call a rational function that looks like this. Okay, so here's f of -1. Here's f of +1. The question says, are we guaranteed to touch 0 or y value of 0 somewhere in between? And we can see we never touch a y value of 0. This function does not have an x-intercept anywhere. between -1 and 1, and the reason why is because this function is not continuous. Okay, so what we would have to say here is this function is not continuous at x equals 0, therefore we can't apply the intermediate value theorem. Okay, so that means that the intermediate value theorem does not guarantee a solution where we touch a y value of 0 between -1 and 1 due to the fact that we're not continuous over that interval. So the continuous part really does matter here, and we have to state that continuous part first. We have to state that the function is continuous before we can start using the intermediate value theorem. Okay, a couple other little examples here that I want to show you, and then we'll be done with this video. So real quickly, let me draw a chart. Okay, let's say for our x values, we had -1, we had 5, we had 7, and then we had 13, and then we had 2. For the y values, sorry, we have -2, 3, 7, and 0. Okay, so this is our chart that we're looking at right here. And let's say that I posed the question, or let's say I told you f of x is continuous along the interval from -1 to 13, the closed interval. Okay, and then I ask at least how many times is f of x equal to 1 along the interval. Okay, at least how many times is f of x equal to 1 along the interval. Now, some students are going to draw a picture for this, and if you want to draw a picture for this, this is fine. Okay, here's kind of what we're looking at. I'm going to draw a very rough sketch. -1, -2. Okay, we have a point at 5, 3. We have another point at 7, 7. And then we have another point at 13, 0. And the question here says, how many times are we going to touch, at least how many times are we going to touch a y value of 1 along this interval? And you can kind of draw a picture here and get an idea of it. Okay, now we don't know if that's exactly how many times this is happening, but we can at least kind of see that if we're continuous along this interval, we have to cross through y equals -1 at least 2 different times. So let's see if we can justify this using the intermediate value theorem. Now, the first thing that we need to state here is that f of x is continuous along the interval. Okay, if you don't state this, we can't use the intermediate value theorem, but I'm going to go ahead and state this even though it was given to me in the question. And now we can write some different things right here. Okay, so we could say that f of x, or let's see, let's be a little bit more specific right here. We could say between x equals -1 and x equals 5, f of x equals 1 at least once, because f of -1 equals -2, and f of 5 equals 3, and -2 is less than 1, which is less than 3. Okay, so the y value 1, which is what we're trying to get, is in between where we started and where we ended. Okay, let's see. If we wanted to go through every interval right here, we would have to say between x equals 5 and x equals 7, f of x does not equal 1, sorry, I should say f of x is not guaranteed to equal 1 at least once, because f of 5 equals 3 and f of 7 equals 7. And I know this sounds obvious, but we would have to say and 1 is not between 3 and 7. Okay, and then we could wrap this up by saying between x equals 7 and x equals 13, f of x equals 1 at least once, because f of 7 equals 7, and f of 13 equals, I believe the value was 0. okay? And we could say that 7 is greater than 1, which is greater than 0. Okay, so once again, that y value lies in between where we started and where we ended. So therefore, f of x equals 1 at least twice. We just showed the 2 times along the interval from -1 to 13. Okay, so that's a very detailed answer there, but that's showing, using that intermediate value theorem, why we have to touch it at least twice. It has to happen once between here and here. Okay, so to get from -2 to 3, I got to cross through 1. It does not have to happen between here and here, because I don't have to cross through 1 to get from 3 to 7, but then it does have to happen between here and here, because I have to cross through 1 at least once to get from 7 to 0. Okay, so that's one example of where we could use the intermediate value theorem to guarantee some particular solutions. Now, you might get asked something with a calculator here, and so we'll close by trying this. Okay, so let's look at this function. F of x equals, let's go 5 to the x minus 2 plus the sine of x minus e to the 2x plus 3. And so my question is, and this is a calculator question. Okay, so I'll show some calculator work on the screen, but we'll say, does the intermediate value theorem guarantee that f of x has a root? And remember, root means like a 0 or an x-intercept between -1, the closed interval, -1 and 2. And we want to explain our work. Okay. Now, the first thing that we're going to have to do in order to figure this out is we're going to have to decide, is this function continuous from -1 to 2? Now, let's break down each individual piece of this function. 5 to the x minus 2, that is an exponential function. This is continuous everywhere. Okay. If I look at sine of x, that's a wave. This is continuous everywhere. If I look at e to the 2x, that's also an exponential function, although this part's negative, but it's an exponential function. So this is continuous everywhere. And if I look at the number 3, that's just a flat line. That's continuous everywhere. Okay, so guess what? If I take a bunch of continuous pieces and I add or subtract them all together, I get something that in the end is still continuous. Okay, so I'm going to go ahead and start this by saying, since each piece of f of x is continuous everywhere, which doesn't necessarily need to be the case, but all these functions that we picked here are continuous everywhere. We can say that f of x is continuous along the closed interval from -1 to 2. Okay. Each piece of this is continuous everywhere, and when I say each piece, I'm not talking about a piecewise function. I'm just saying if I took each element of this function and added them all together, if I take a bunch of continuous elements and add or subtract all of them, I get something that's continuous when I'm done. So we can use the intermediate value theorem here to try to figure this out. Okay. So the next thing that I would want to do is I would want to think about, well, what's f of -1 and what's f of 2? Because guess what? If we start above or below 0 and we end on the other side of 0 for y values, then that means that we have to have a root somewhere in between -1 and 2. So let's go ahead and let's try this. I'm going to pull up a calculator here on my screen. I have already gone ahead and inputted this function. Please make sure that your calculator is in radian mode, because we're working on something that's trigonometric here. And I'm just going to show you guys a quick calculator shortcut. So if I go second and quit to get back to the main screen, if you press alpha trace, it's going to bring up all of these different functions. Now we inputted our function into y1, so I'm going to select y1. Okay, and if I put a set of parentheses here and I put -1, this is going to evaluate the function at -1. Okay, so there's the value at -1. And then I could do the same thing to see the value at 2. Okay, oops, sorry about that. So if I take the value of this function at 2, here's what I get. Okay, so let's go ahead and write these down. So we'll round to 3 decimal places. That's what the AP test requires. So y of -1 is 2.031. Okay, 2.031. and y of, or f of 2 is negative 49.689. Negative 49.689. Okay, so I've gone ahead and I've looked at these values, and what we can say here is, hey, it looks like we started above 0 and we finished below 0. So therefore, we could say f of x has a root between negative 1 and 2 because f of negative 1 is greater than 0, and 0 is greater than where we finish at f of 2. Okay. And really we should say, before we even start this, we should say by the intermediate value theorem. Okay, so let me amend this just a little bit. Scoot this over so we can give a full answer here. By the intermediate value theorem, f of x has a root between negative 1 and 2 because we started above 0 and we finished below 0. Remember, in order to use the intermediate value theorem, the first thing that we have to do is we have to state that the function is continuous. Then we have to show what we're looking for. Are we starting above or below, whatever solution we're looking for, and are we finishing on the other side of it? If those things are true, then we can have a concluding statement where we use the intermediate value theorem to prove the existence of a solution. All right, so that's the intermediate value theorem for you. Hopefully this makes sense. Remember, we have an assessment coming up next week. We'll do a little bit of review on Monday. Thanks. Bye.